Hello and welcome back. We're going to be talking about some examples of finding Maclaurin series for variants of the functions that we have listed here. We've seen in previous videos the first and fifth Maclaurin series that you see here, the ones for 1 over 1 minus x, that's summation n equals 0 to infinity, x to the n. It's a variant of the geometric series, or it's the geometric series written in a variable form. And then from that, we got Maclaurin series for the inverse tangent function. We saw that in an earlier video as well. So just a reminder, the interval of convergence for the power series for 1 over 1 minus x is minus 1 to 1, and it's a little bit more for tan inverse of x. I haven't showed this in a video, but it turns out the interval of convergence includes 1, and I will probably talk about this in a class sometime about how we can use the inverse tangent function expansion at 1 to come up with an approximation for pi. And then in class, I've derived the Maclaurin series for e to the x, sine x, and cosine x, and we commented that for all three of these functions, the interval of convergence is all real numbers. So we want to keep that in mind from time to time as we go through some examples. And so we're going to be looking at these 5 formulas and coming up with power series expansions, Maclaurin series, for variants of those functions. So here, let's get to the examples. First off, we're going to find a Maclaurin series for the function e to the minus 3x. So again, just a reminder, e to the x has Maclaurin series summation n equals 0 to infinity, x to the n over n factorial. And so the thing that's going on here in this example is that we've replaced x with minus 3x. And so I'm going to put minus 3x in where x is in this power series expansion. Excuse me, I don't want to do that. So e to the minus 3x is going to be summation n equals 0 to infinity minus 3x to the n over n factorial. And at some level, we could leave it this way, but it's probably a little bit better to write it at least as an alternating series. And I could even pull this 3 to the n out. And so I could write it as summation n equals 0 to infinity minus 1 to the n, 3 to the n, x to the n over n factorial. And that's it. That's our Maclaurin series. Our next example is for the sine of x squared. So we remind ourselves that sine of x is summation n equals 0 to infinity minus 1 to the n, x to the 2n plus 1 over 2n plus 1 factorial. And again, all we're doing is we're doing a little bit of replacement. And so here I've got x squared in for x. Let's do it. So again, sine of x squared is going to be summation n equals 0 to infinity minus 1 to the n, x squared to the 2n plus 1 over 2n plus 1 factorial. But again, we should not leave it that way. We can multiply those exponents together and get summation n equals 0 to infinity minus 1 to the n, x to the 4n plus 2 over 2n plus 1 factorial. And that is our answer. Next one's a little bit more involved. We want to find a Maclaurin series for the integral from 0 to x of tan inverse of t over t dt. So we start again with our building block. Tan inverse of t is going to be summation n equals 0 to infinity minus 1 to the n, x to the t to the 2n plus 1 over 2n plus 1. And so tan inverse of t over t I can just divide each term by t, and that's going to cancel out 1 power from this numerator. So I'm going to cancel that out, and that's going to kill that off. And so I get summation n equals 0 to infinity minus 1 to the n, t to the 2n over 2n plus 1. And so now I'm ready to do the integration. And so I would integrate the series I just wrote down. But we remember that we can switch the order of summation and integration here. And so I'm just going to integrate this termwise. I add 1 to the power and divide by the new power. And so it's going to be summation n equals 0 to infinity minus 1 to the n, t to the 2n plus 1. And if I've got 2n plus 1 down there already, I'm going to wind up with 2n plus 1 squared. And I evaluate that between 0 and x. When I put x in for t, I get this. X to 2n plus 1 over 2n plus 1 squared is my general term. And if I put 0 in for all the t's, I'm just going to be subtracting 0. So it's as if it really isn't there. And so this is my answer right here. So we can manipulate the Maclaurin series that we know, and then we can integrate termwise. We saw that in previous videos. And then here we're just evaluating at x and evaluating at 0, and this is our result. Our next example is j of x equals x squared cosine of x to the 4th. We've got a couple things going on here. We'll start off by remembering that cosine x is this. And so cosine x to the 4th, I'm going to, as I've noted previously, I'm putting in x4 to the 4th in for x. And so I get summation n equals 0 to infinity minus 1 to the n, x to the 4th to the 2n over 2n factorial. And so x squared cosine of x to the 4th, I'm going to multiply each of those terms by x squared. And now I think about this for a little bit. X to the 4th to the 2n, I'm going to multiply these exponents. That's just x to the 8n. And I'm going to add 2 to all the exponents. So we get minus 1 to the n, x to the 8n plus 2 over 2n factorial. And so that's x squared cosine of x to the 4th. And now our final example is going to involve the alternating series remainder estimate. And we're going to take the function that we just found the power series expansion for, and we want to approximate the integral between 0 and 1 of that function to within 1/100,000th of its actual value. So let's take a look at that. We already know, we've already done some work here. So the integral from 0 to 1 of x squared cosine of x to the 4th dx is going to be the integral from 0 to 1 summation n equals 0 to infinity minus 1 to the n x to the 8n plus 2 over 2n factorial dx. As before, I can switch the order of summation and integration. And then I integrate again using the power rule. If I add 1 to the exponent, I get x to the 8n plus 3. And I'll divide by the new power as well. Sorry, I've got that wrong. And I'm evaluating between 0 and 1. When I put 1 in for x, I just get 1 to the 8n plus 3. That's always 1, no matter what power I raise it to. When I put 0 in, 0 to the 8n plus 3, that's always equal to 0. And so the series that represents this integral, is going to be 1 over 8n plus 3, 2n factorial. This is an alternating series. I can write that a little bit better. It's an alternating series, and so I'm going to be applying the alternating series remainder estimate to approximate this. Alternating series remainder estimate. Okay, well, let's see what we can come up with here. B sub n is that. So b sub n plus 1 is going to be found by replacing n with n plus 1. But I can do some distributing here. I'm going to get 8n plus 11 times 2n plus 2 factorial. And so my remainder estimate says if I want to make my remainder less than 1 over 100,000, our goal is to make b sub n plus 1 less than 1 over 100,000. I like to flip things over, so let's make 8n plus 11 times 2n plus 2 factorial bigger than 100,000. I don't need to go very big, so let's take a look at n equals 2. If I let n equals 2, I get 16 plus 11 is 27, and then 4 plus 2 is 6, so I have 27 times 6 factorial, which isn't big enough, it's a little under 20,000. But when n is equal to 3, I get 24 plus 11, 35, 2 times 3 plus 2 is 8 times 8 factorial, and that actually is well over 1 million. These numbers grow fast. And so I want to take n equal to 3. So I'm running out of space here. Let me carve out some space here for this problem. It'll be kind of short. So what I wind up getting is my approximation is summation n equals 0 to 3 minus 1 to the n, 1 over 8n plus 3 times 2n factorial. And so that's the approximation to the integral to within 1/100,000th. And so I could go ahead and tell you that if I write out those four terms, I get 1 over 3 times 0 factorial minus 1 over 11 times 2 factorial plus 1 over 19 times 4 factorial minus 1 over 27 times 6 factorial. And that is my approximation to the integral from 0 to 1, x squared cosine of x to the 4th dx. I said that was my final example, but I was wrong. I've got one more. Let's find the sum 1 minus 2 plus 4 over 2 factorial minus 8 over 3 factorial plus 16 over 4 factorial minus 32 over 5 factorial plus ... So we've got hopefully enough information here to write this in some sort of summation form. And I'm going to go ahead and put that over 0 factorial and that over 1 factorial. So hopefully I can see that, let me write this as an, I'll write it as an n. Summation n equals 0 to infinity. The bottom is just going to be n factorial. And hopefully I can recognize that I've got an alternating sum here, minus 1 to the n. That's going to give me a positive first term. And then 1, 2, 4, 8, 16, 32, we want to recognize that those are powers of 2. So this is 2 to the 0, 2 to the 1, 2 squared, 2 cubed, 2 to the 4th, 2 to the 5th, so this is 2 to the n. Or summation n equals 0 to infinity minus 2 to the n over n factorial. Well, that sounds like an exponential function to me, and in fact, it's e to the minus 2. And so we were looking at this series in earlier sections, and now we're seeing that that really is just the number e to the minus 2.